So you might be wondering, what is a lava lamp? A lava lamp is just a tube filled with bright colored liquids that are constantly moving. They work because of some very interesting chemical reactions between the liquids inside the lamp, which we'll learn about a little later. The best part about lava lamps is that you can make one yourself at home, and we're going to show you how. Through this project, we're going to learn about chemical engineering. Chemical engineers use chemistry, physics, and math to produce food, fuel, and medicine. To become a chemical engineer, you can choose to major in chemical engineering at a university like UT.
Hey, what's going on everyone? Today we're going to have a little crash course about density. And all density is how much space an object takes up, its volume, in relation to the amount of matter in that object, its mass. And density's got a pretty simple equation. All it is mass divided by volume. So I got a couple things here. I got a bowl of water, I got a lemon, I got a quarter, I got an ice cube. So we're gonna do a little experiment right now just to make a little more sense of it. I'm gonna go ahead and drop the lemon into the water. And as we can see, the lemon floats. Move it around there. So what does that mean? That just means the lemon has a lower density than water. Therefore, it will float. So let's take this out. Let's drop the quarter and let's see what happens. So we take the quarter, we'll drop it in. It sinks. That means the density of the quarter, or of the metal in the quarter, is higher than the density of water. So I got a little tricky one for you. So I got a thing of ice, and we know ice is made out of H2O. It's just water, frozen water. So if I put it in there, what do you think's gonna happen to it? Let's find out. As you can see, the ice floats on water. And the reason it does that is because when water freezes, it expands a bit, therefore increasing its volume, but keeping the same mass. So the density of ice is just a little bit lower than the density of water.
Polarity describes the spread of electrons in a molecule. Polar molecules have a lot of electrons on one side, but not the other. Nonpolar molecules have electrons spread around evenly. Some bigger molecules have one nonpolar side and a polar side. Polar molecules like to stick together with other polar molecules, kind of like this. Nonpolar molecules also like to stick together with nonpolar molecules. However, nonpolar molecules don't like to stick together with polar molecules. That's why water and oil don't mix, because oil is nonpolar and water is polar.
Another key concept our project shows is a chemical reaction. A chemical reaction is when one or more substances are changed into different new substances. An example of this is when you're baking. When you bake, you start off with flour, sugar, milk, eggs, and other ingredients. And when you put the batter in the oven, a chemical reaction occurs and you get a completely new substance out, in this case, a muffin. A key thing to note is that chemical reactions are not easily reversible. For example, you can't get back the eggs you used to make this muffin once the muffin is already made. There are certain things that can give you hints that a chemical reaction has occurred. These signs can be color change, the release of gas, and temperature change. When you burn wood in a campfire, that is a chemical reaction because the wood changes into ash. The ash is black, showing a color change, and the burning wood gives off both smoke and heat, showing the release of gas and a temperature change. In our project, we are using Alka-Seltzer tablets, which is made of citric acid and sodium carbonate. When it dissolves, it reacts with the water to make carbon dioxide gas. The gas is released in the form of bubbles, which is a great sign of a chemical reaction, and this is how our lava lamp works.
So how exactly are you going to build a lava lamp at home? First, you'll need a clear, disposable bottle. This could be an old water bottle, an old dish soap container, or even a jar, like something that used to hold pasta sauce. Next, you'll need an Alka-Seltzer tablet. If you don't have Alka-Seltzer tablets, you can purchase them at any drugstore or grocery store. Or you can also look to the end of our presentation for an alternative version using table salt. Next, you'll need an oil. We recommend vegetable oil, but other oils like canola oil and olive oil should work fine. In order to get a nice colorful lava lamp, the next thing you'll need is food coloring. And lastly, you'll need water. Let's get started.
First, you're going to take your bottle and you're going to fill it about 1/4 of the way with water. A little more, like so. Then you're going to add your food coloring, and I would add about 5 to 10 drops. You can do any color you want. I'm going to try and make orange for UT Hook'em Horns. So we'll do and try and do maybe around 5 to 10 drops. Last, you're going to fill the rest of your bottle up with vegetable oil, or any oil you have on hand. And then you're just going to wait for the bubbles to settle.
Alright, at this point you should have your vegetable oil, your water, and your food coloring within the water bottle. And the next step that we're going to do is add an Alka-Seltzer tab. A half tablet should work fine, but make sure that once you put it in, you don't close the cap until the tablet fully dissolves so we don't have a pressure buildup. So once I put it in, you can start to see the chemical reaction taking place with the Alka-Seltzer tab and the water forming carbon dioxide gas. So you can see the little bubbles right here. And we're gonna wait until it dissolves, and then we can close the cap back up. And you can see that this chemical reaction is forming this circulating lava lamp effect with the little bubbles right here.
Hey guys, so your lava lamp should look like this right now. So what I'm going to do is I'm going to turn off the lights and show you what it looks like when the lights are off. It looks like a real lava lamp that you'd actually buy. Okay, so it glows and it looks like lava. So I'm going to go ahead and add another seltzer tablet. Okay, and so as it starts bubbling, the lava starts rising, right? So what's happening here is the gas that's being released by the seltzer tablet is causing the denser water to rise into the less dense oil, and then as it gets the top away from the bubbles, the water is going to fall back down and it looks like lava rising and falling, just like a real lava lamp, right? And it's glowing. So now what you can do is you can also decorate your bottle, be creative. You could add glitter to it, change the color with some more food coloring, just really have fun with it, because now you have a fun lava lamp. After you have fun playing with your lava lamp, like I just did, what I'm going to show you is what happens when you add soap. So we talked about polar and non-polar molecules already, right? And so the reason that the oil and the water don't mix is because water's polar and the oil is not polar. But soap is both polar and non-polar. The molecule is both. So I'm going to show you what happens when we add some soap to our lava lamp and mix it up. So it's all mixed. And if you were to mix it before, what would have happened is the water and the oil would have separated. And what's happening now is that's not going to happen, because the soap is interacting with the oil and the water, and since it's both polar and non-polar, they're not going to be able to separate now because of the chemical interactions. But hopefully you had fun making your lava lamp and decorating it, and I hope you go and check out some other projects.
So, what did we learn? First, we learned that oil does not mix with water. Why did this happen? It happened because oil is nonpolar, while water is polar, so they are insoluble in each other and don't mix. We also saw that the Alka-Seltzer tablets dissolved in water. The tablet contains sodium bicarbonate, which is polar, and water is also polar, so they are soluble and do mix together. Lastly, why did the oil float in the water rather than sink? This is because of density. The oil floats because it is less dense than water.
Another thing we learned is the difference between chemical and physical changes. A chemical change happens when one substance turns into an entirely new substance. We saw a chemical change when the Alka-Seltzer tablet dissolved into the liquid to produce carbon dioxide gas. Another example of a chemical change is burning wood to ash, because it forms something completely new. A physical change happens when a substance changes size or shape. An example of a physical change is cutting a lemon, because the lemon slice is still a lemon even after it is cut.
So why did the oil and water mix once you added soap? This is because soap is a molecule that has both a polar and a nonpolar end. Because of this, it is attracted to both oil and water. So when you add it to your oil and water, it acts as kind of a bridge that allows them to mix.